So the goal today is to fulfill a promise I have made to several students over the years of proving Stirling's formula. And so I've given half proofs of it many times. Today I want to do it fully. The other reason to do this is rather than proving Laplace's method in full generality and writing down exactly what conditions we need on the functions phi and c, let's do it for a specific example. And then as we go through the calculation there, we'll see what we need. And you'll get natural conditions on phi and c. In my youth, when I was an undergraduate, I wanted to prove theorems in the greatest possible generality. Why would I assume my function is in the Schwartz space and decays rapidly and is infinitely differentiable? And then eventually you realize that math is not just doing homework problems. You actually want to solve things people care about. It's like, well, of course my function is going to be infinitely differentiable and will be rapidly decaying. This is not a big assumption, because you're actually using the results to prove things of interest. And so instead of going through the more general conditions, I thought, let's concentrate on a specific case. So what we're going to look at is the gamma function. And there are natural reasons why we would define it this way. So we're defining gamma of s to be the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx, or the integral from 0 to infinity e to the minus x, x to the s dx over x. The advantage of writing it like this is now if you rescale x by a factor of 5 or 6 or 7, the dx over x, that measure is invariant. And then you're looking at the integral against this function. Okay? So the goal is we want to somehow convert this to something of this form and then apply Laplace's method. So for us, I'm going to assume that s is greater than 0. So I'm going to assume s is real value. The book talks about how to handle the case when s is complex. Not surprisingly, in a complex analysis class, you probably want to be able to handle the case when s is complex. There are two issues. One is analytically continuing this formula. Well, we've got a formula that already works for real value of s. As long as it converges for complex values of s, it has to be the unique continuation, because if you look at their difference, there's 0 when the real part of s is real and positive. If you have two functions that agree on a set of points that accumulate, what do you know? They're equal. And we're going to use that idea crucially when we get to the central limit theorem. So that's one place where the complex analysis comes into play. The other, not surprisingly, is actually putting in a complex number for s. One of the most important cases to look at in something like this is when s is pure imaginary. So there you would have something of phase. And this would get into Fourier series, Fourier transforms. We'll talk about those in a little bit. The larger s is, especially if s is, say, I times t, the more rapidly, if you look at the cosine and the sine, the more rapidly it's oscillating, the shorter the period is. The shorter the period is, if your function c is smooth, if it's oscillating very rapidly, then this function is going up, down, up, down, up, down, up, down, or positive, negative, positive, negative, positive, negative, positive, negative. And you're going to have massive cancellation in the integration. So that as long as phi of x is away from its minimum value, you're going to be getting an enormous amount of oscillation, and the integral should be small. Most of the contribution should be from the minimum value. Okay, and in a lot of this, we always try to pull out the phi of x naught. There's really no loss in generality in that. That's just changing a function phi by subtracting and adding phi of x naught. All right, so we want to start making this look like that. So there's a couple of issues. Right? So the first issue is, we have a x to the s, we have an e to the minus x. We can write this as the integral from 0 to infinity of e to the minus x. I can write x to the s as e to the s log x. So we can bring that up here, and that would be plus an s log x, x to the minus 1 dx. And again, we don't have that many tricks in mathematics. By putting it in the exponential, this is a really good way to analyze things. Unfortunately, we're supposed to have something in the form s times phi of x. We don't have s hitting everything, we have only s hitting some things. So we somehow have to change variables in such a way that we can write this as s times something. So the natural change of variables is to replace x with s times x. If we do that, we'll have a log of s times x here. That'll give us an s log s, but that's fine. We can just pull that outside. And if you think about what Stirling's formula says, gamma of n plus 1 is n factorial, is about n to the n, e to the minus n, square root of 2 pi n. We're roughly aiming for something like that, but the role of n is going to be played by either s or s plus 1 or s minus 1, something like that. So this is Stirling's formula. We would expect to see something in the form n to the n, e to the minus n. Well, another way of writing n to the n, e to the minus n is this piece is just e to the negative n from here, and then we'll have a plus an n log n. So we have like an e to the n log n. We expect a term like that. If I replace x with s times x, we'll get an e to the s log s. That's going to look a lot like the e to the n log n term. So in terms of just getting some idea of how you can do this algebra, if we hadn't done anything before, if we didn't see that, we've done elementary arguments in the past, at least if you've taken classes with me, on the size of n factorial. Should be about n to the n, e to the minus n. You can do this with the integral test. They sometimes do this in calculus classes. It suggests we want an s log s, so this is a good change of variables to be doing. All right, so hopefully that's enough motivation. So we're going to let x go to s times x. In upper level math classes, as this clearly is, you overload variables and you'll have x be s times x. In other lower level math classes, you would use a different variable to try to minimize confusion. We no longer care about minimizing confusion once you reach this point. We embrace it. Okay, so now we get gamma of s is equal to the integral from 0 to infinity, because remember, s is greater than 0. And now we have e to the negative sx plus s log sx. Now over here we have x to the minus 1 dx. What does x to the minus 1 dx become? Same thing. That's the whole point of having the invariant measure. That's why we define the gamma function in this annoying way. By defining it like this, we now have the advantage of dx over x is unchanged. So it's 1 over x dx. And you can begin to see what our function c is going to be. Our function c is probably going to be 1 over x. All right, so we can pull out the s log s. So we have e to the s log s. Integral from 0 to infinity. E, now we want to have a minus, so we pull out a minus s, and we have an x minus log x. So please be watching to make sure I do not make algebra mistakes, or it's going to be a painful lecture. All right, I think I've pulled things out correctly. We've put out the s log s. We have a s log x that's going to be with a minus sign. So this is suggesting our function phi. So the calculation is going to be wrong, but let's try, phi of x should be what? I'm sorry, x minus log x. And phi prime of x will be 1 minus 1 over x. And then phi prime of x equals 0 means x equals 1. And then if x equals 1, we get phi of 1 equals what? 1. So this is not what we want. We want to have things so that phi of the minimum point, called the minimum point x naught, we want phi of the minimum point to be 0, phi of the minimum point is 1. How can we fix this? Yeah, shift it. So what do we need to shift it by? I'm sorry? Yeah, so if we put in a minus 1 and then add a minus and then add a 1, we should be okay. So let's do x minus 1 minus log of x plus 1. That's not going to change the derivative. Not going to change where the derivative is 0, but now phi of 1, well, no, phi of 1 will still be 1. So what we do is, when we shift it, we'll define this to be phi of x. So if we define this to be phi of x, now we will get phi of 1 is 0. But we're going to get an extra factor up here. Okay? So what we're going to do is we're going to come up over here, and we're going to write this as x minus 1 minus log of x plus 1 over x dx. When we do it like this now, this is going to be our phi of x, and we have an extra 1 over here. But notice there's no x dependence. We can pull it outside the integral. And what is hitting it? A negative s. Oh, that's going to be an e to the negative s term. That's the piece we were missing over here. Again, we do not have to do this. We could have kept it so that phi of x naught is equal to 1 and not 0. But I really like this idea of localizing to where the action is, normalizing it so that the value is 0 there, and then you just pull out the main term. And so now we get that this would equal e to the negative s plus s log s times the following integral. The integral from 0 to infinity of e to the negative s phi of x c of x dx, where phi of x is going to be x minus 1 minus log x, c of x is going to be 1 over x, and our special point x naught is 1, and phi of x naught is 0. Okay. Any questions on what we've done up over here? So we're now basically in a situation where we can apply the method of stationary phase. Right? We have our functions. Are there any concerns or worries you have?
Yeah, the a to b versus 0 to infinity.
Right. Now, we're integrating from 0 to infinity. If we restrict to just a small window around 1, that should be where the meat of the contribution is. And so in fact, if we go a little bit before or a little bit after, we should be okay. What concerns might you have, though, when you're trying to do this integration? So first thing you should do whenever you have an integral, is it finite? So what's the decay of c like? 1 over x. C is not decaying rapidly. So are you concerned about going off to infinity because c is not decaying? Not at all. We've got an exponential here. If you look at phi of x, when x is large, yes, we have this little bit of log of x that we subtract off. But once x is even modest, this is going to be at least 1/2 x. You then multiply by a huge positive number, and you have an extremely large exponential factor with a minus sign. So this is going to have exponential death. It's going to be absolutely fine that 1 over x is not decaying rapidly. Any other issues with 1 over x?
0.
So we have problems near 0 as well. So are we worried about what happens as x gets near 0? Because now, unfortunately, as x gets close to 0, oh dear, x minus 1 is looking like negative 1. Oh dear, that becomes an e to the positive s. Yes?
The log x term.
Yeah, the log of x term will then save us, right? So even though this x minus 1 is going towards negative 1, the log of x, because x is going to 0, is going towards negative infinity. The negative in front of that makes it go to positive infinity. The negative over here, 3 negatives end up reinforcing, and it's going to look like e to the negative very large number times s. So we will still have huge exponential death, so we're going to be fine. So what you need to do now is, if you're going to prove things carefully, you want to actually do some of these integrations. So you want to integrate maybe from epsilon to alpha, say e to the negative s phi of x 1 over x dx. And just try to see what's the contribution going to be in this range. Now we know the minimum value of this function is at x equals 1. So we'll take alpha to be less than 1. Let's calculate phi double prime. What's phi double prime? We should have done this earlier. I'm sorry? 1 over x squared, which is always greater than 0. Which is one of the conditions we needed. We needed phi double prime to be greater than 0 so that it looks like a parabola, so that this is really a minimum. So in fact, what this means is if we wanted to plot, here's x, here's 1, phi of x is going to look something like this, with its minimum like this, and the further you go off to the left or the right, the larger it's going to get. So if I want to integrate up to alpha, I can approximate this whole thing here by just the value of big phi at alpha. Right? So this integral would be less than or equal to the integral from epsilon to alpha e to the negative s phi of alpha 1 over x dx. Yes?
Can you explain that step again? Why is that like a decent approximation? Why is that an approximation?
Well, so phi is increasing as we go to the left before 1 and increasing as we go to the right after 1. This is one of the nice things about having phi double prime greater than 0. So if I want to look at where's the smallest value of phi of x in the range from epsilon to alpha, since alpha is less than 1, the smallest value is at alpha. And so if I put in the smallest value, that will give me the smallest exponent over here in absolute value. So that will give me the smallest exponential death. So again, we're being crude in the approximations because we can afford to be crude. It's going to be so small that this is absolutely fine. And so if we wanted to look at what the contribution of this would be, this is going to be an extremely large negative number as s goes to infinity for any fixed alpha. How large could 1 over x be if I integrate over this region? What could we do to estimate the integral of 1 over x? Yes, we could bound it by 1 over epsilon, or we could even bound it by the log of epsilon if we wanted to. And so we can bound this by, it's less than or equal to e to the negative s phi of alpha times the log of epsilon. No, it doesn't want to swing. All right, and so if we wanted to try to estimate how much of a contribution this is, we would eventually want to let epsilon somehow depend maybe on s. Yes?
Do we need absolute value of log of epsilon? It's going to be very
Yes, you're right. We should put an absolute value like that. Yes, because it'll be the log of alpha minus the log of epsilon, and the log of alpha is less than 1. Right. So we would have a bound like this. So in terms of the size of this term, this is going to be much, much smaller than our main term, so long as alpha is a fixed distance away from 1. The question then becomes, what if we start letting alpha creep up on 1? As alpha creeps up on 1, what's happening over here? Well, as it creeps up to 1, phi is getting closer and closer and closer to 0. And the closer that gets to 0, the less exponential death we have. And the larger things are going to be. So now, if we start having things get very close, we now start to get into trouble. But if we stay a fixed distance away, And this was a lot of the arguments in the book, is that we have some interval a, b that contains the point we care about. So if we choose some alpha less than 1, we can easily restrict the integration to epsilon to alpha, and the amount we are contributing from here is negligible for any fixed alpha. We could let alpha approach 1 at some growth rate depending on s. And then the question is exactly how fast. If it's 1 over s, I would start to be worried because we expect the integration to be contributing on the order of a window of size 1 over s, or maybe 1 over square root of s. So somewhere around there, I would be concerned. And if it was, 1 over s to the 1/4, to me that's so much further than 1 over square root of s, I'm not worried at all anymore. But so the idea is for fixed alpha, we're fine. So OK for fixed alpha less than 1. And that was one of the things we needed. Now the problem is we want epsilon to go all the way down to 0. So now we would need to consider what's going on as we take the limit as epsilon goes to 0. So one of the things you learn to do in number theory is you break a really big problem into lots of smaller problems. Why didn't we do the interval from 0 to alpha all at once? So now we also have to do the integral from 0 to epsilon of e to the negative s phi of x 1 over x dx. Or if you want, maybe call it epsilon. Should we use delta? Should we use eta? Should we use epsilon tilde? What do you want to use? Delta? We'll use delta. First loud voice wins. Limit delta goes to 0 from above. So the plus sign means we're coming from above. Why would we want to break it up like this?
This is harder because things go to infinity. It's easier because everything is still nice in that region.
Okay.
We're kind of in a region where there's bad behavior on both ends, and when we're doing the integration, we only want bad behavior on one end.
Good. So we have a region where we have trouble in both places. We have trouble as we get close to 1, and we have trouble as we get close to 0. So the idea is by splitting the integral into 2 different regions, we can do different approximations depending on where we are. If we're near 1, we've got to be a little bit careful. Well, as long as we stay a little bit away from 1, we'll have a decent cancellation from here. But we're using a bound that works everywhere. And so now as we get further and further down, as we get closer and closer to 0, this bound still works, but this becomes a worse bound to use. And so what we can do here is in an interval like this, we could actually now approximate this by choosing x to be epsilon, because that's going to be the largest value. And so the question then becomes, how rigorous do you want to do this? Eventually, when you become a professional number theorist, you don't even do these calculations at all. You just say clearly it's negligible. It's a wonderful day when that happens, and you can just write that. So the question is, how would we carefully write that this is negligible? The problem is we have this function 1 over x.
Use the capital psi? Capital, what is that? Phi? Capital phi of x? Use it.
Okay.
The log is going to dominate.
So the log is going to dominate. And so one thing is to try to actually just replace this with a really good bound. So the other thing we could do is we could go from epsilon to epsilon over 2, and then epsilon 2 to epsilon over 4, epsilon over 4 to epsilon over 8. We could do a dyadic decomposition. In each one of these, we could get a good bound, and then we could sum them all together. So that's one approach, is to just keep splitting it into smaller and smaller intervals, and in each one of these intervals, we have a decent bound. The other thing is to say, well, we can actually unwind what phi is. Phi of x is x minus 1 minus log of x. Well, when we become very small, phi to the x is looking a lot like negative log x. Okay, well, then we would have e to the negative log x that becomes x to the s. Oh, well, great. We've got an x to the s. S is going off to infinity. That's going to clearly kill the x minus 1. Right? So if we want to look at negative, we have s, then we have x minus 1 minus log of x. This is equal to s log of x minus x plus 1. And I claim if x is really, really small, let me make sure I'm doing this right. Do we lose a minus sign? I'm just wait a minute. I'm worried now that we've made a slight mistake. We had log x with a positive sign. So as x,
When delta log just becomes super negative,
right, but now I'm afraid as x gets closer and closer to 0, the log of x is going to negative infinity. Oh, which is fine because we have e to the negative infinity. Okay. Okay, that's fine. Oh, okay. The algebra is just a little bit worse than I had hoped for, but that's fine. The other way to look at it is we can write x, 1 over x as e to the log x, which might be an easier way to do it, and incorporate that inside. But the idea is eventually this will be at least an s halves log x. And then that's going to be absolutely fine. But I think it might be easy to just write 1 over x as e to the x log x. As e to the log x. And then if we incorporate that in, we'd have like a 1 over s over here. So that might be a little bit faster. And so we would have 1 over x is e to the log of x. So our integrand, negative log x. The limit as delta goes to 0 from above, integral from delta to epsilon, e to the negative s. And now the phi of x is going to be x minus 1 minus log of x. And now when we bring this inside, we multiply by negative s and we divide by negative s. And so now when we bring this inside, the negative and the negative reinforce, we get plus a 1 over s log x. So now when we look at the integrand, we now have the limit as delta goes to 0 from above, the integral to delta to epsilon, e to the negative s. All right, now let's look at x minus 1. X is between 0 and 1. The larger x is, the more cancellation we get. So if we drop the x, I claim we're only making things worse for us. So do we agree that we can just drop the x over here? That's going to just make the function larger. So we would get a 1 minus, and when s is huge, do we agree that 1 over s is going to be at least 1/11 or 1/10 or something like that? And so I want to see we would have something like this. So let's see. So we should have had the limit, an s log x, which is going to be a very huge negative number. Now we have something a little bit less than that. We only have 9/10 of that. Right? Yes?
Is it negative?
Negative 1, yes. So do we agree with something like this?
Why did you drop the x again?
Well, just, I mean, in this range, I'm going to have some negative exponent. And, x is already so small, x is already so close to 0. X is, at most epsilon. That I'm not really changing things that much by dropping the x. And now when I look at what I have over here, we have a negative 9/10 to the s. And so now we'll have an e to the s coming out from this part over here, and now we'll have an integral of e to the 9/10 s log x that we'll have to deal with. So, again, there's a lot of different ways of attacking these integrals. It's worthwhile every now and then in your life to just spend some time looking and seeing how do we want to do it. Is this enough to convince us now that the integration is negligible? I mean, we could replace x with the largest value, with epsilon, and we would get an e to the negative s 9/10 log epsilon. And so this part here would be less than or equal to e to the positive s, e to the 9/10 log of epsilon. And then the length of this window is going to be at most epsilon. I'm just replacing this by,
Should be an s.
and with an s, yes, thank you. We definitely need that s. So we could do that. Is this enough to show that things are negligible? We need, I'm sorry?
Sorry, doesn't s go to infinity?
S is going to infinity, but remember epsilon is less than 1, so the log of epsilon is negative. And this quantity here is going to be much larger than that. We need some maybe control on what epsilon is relative to s. So we need some relation between epsilon and s. And if we go back to what we had over here, if epsilon is like 1 over s, we're going to have, we're going to be absolutely fine in terms of the decay. Because if we take epsilon to be 1 over s over here, we're going to get the log of s, and we're going to have e to the negative s times some fixed number. As s goes to infinity, this is going to be much smaller than that. The contribution will be absolutely negligible. So if we chose epsilon to be 1 over s, we would be fine over here. If we choose epsilon to be 1 over s, we'll have an s log s. So we'll be fine. So we'd be okay if we take epsilon, I think, to be 1 over s. So the goal is to just get a sense of how you would attack these integrals, how you would break them up into different regimes, and just what tools and techniques you can use. We don't have to evaluate the integrals well. There are other things we could do. If we write this as e to the negative s log x, we can then write this as e that becomes x to the s, or x to the negative s. So the negative and the negative becomes a positive, right? And this would become x to the s, right? What can you tell me about x to the s? As s goes to infinity and x is less than 1, this is going to be negligible. So another way we could attack this is we could just say, well, look, this part over here is going to just look like x to the 9/10 s. And when we integrate that, well, that's going to be negligible. So there's lots of different ways you could handle this. And I just want to give you a sense of the different techniques you can use. Okay. Any questions on how we handle something like this? So again, the trick is you break it up into different regions where you can then use different properties of the function. As we get very, very close to 0, this is looking like x to the s. Well, in fact, this almost tells us, oh, should we have just gone back to the very beginning? Can you push it a little bit? Thank you. So I have talked to OIT about getting better scribbling. If we come back to the very beginning, let's just go to the integral we were looking at. This is where you can now kick yourself. We did all of this stuff, we did all these change of variables and whatnot. Well, if we look at what's going on near x equals 0, e to the negative x just looks like 1. X to the s, well, when x is close to 0, this is going to be really small. Even though we have an extra 1 over here, if s is huge, this is still x to the s minus 1. So if we just unwind things and just expand things back like this, we'd be fine. So sometimes you want to actually go back to where you were before, or just break things up initially, go from 0 to your other piece. All right, so this handles the case of alpha less than 1. If we wanted to do the case where alpha was greater than 1, would that be much harder? So these batteries were fully charged. Okay, so the problem is the batteries are not swiveling. All right. So I don't even know if the audio is recording now. So I will try to have my... Okay. What if we now want to go from, say, beta to infinity? What would we do if we wanted to go from beta to infinity? We have to do a very similar analysis. Again, it decays faster and faster and faster. The 1 over x is just not quite enough for us to have the decay we want. If we borrow just a little bit of decay from the phi of x, we'd be fine. So it's a nice exercise to go through and show that you can handle the decay going from beta to infinity. That if you were to just do those approximations, it would be negligible. And the idea is we've already pulled out the main term. And now that we've pulled out the main term, we're going to have more and more decay in this as x gets larger and larger and larger. This is exponentially decaying. For very large values of phi is going to look approximately like x. The minus 1 minus log of x doesn't really matter that much when x is huge. So you have something that has enormous exponential decay. The 1 over x just barely doesn't integrate to a finite number. So we don't need that much decay from this. So again, you can break this up into regions. So for this particular problem, the analysis, it's cumbersome. But it's not so bad because in the real world, you would never do it. You would just say it's negligible, it follows from these techniques, you can break it up, and you have the exponential decay. The more of these problems you do, the more sense you get. So if you're thinking that you might actually want to study analytic number theory, then I would suggest as a really good homework problem, do the case beta goes, you integrate from beta to infinity. Because I know not all of you want to do that, I don't want to go into all the details in that, I don't want to do the other case. I'll leave that as, it's your choice if you choose. Happy to talk to you about that, but I want to do just enough so you have a sense. Okay, now let's do the last part. So the last part is now we can assume we have some alpha and beta. And we can say we've reduced it to, we want to integrate from alpha to beta of e to the negative s phi of x 1 over x dx, with alpha less than 1, less than beta, less than 0, less than infinity. We're in some region like this. And this is where we want to say we essentially have a normal distribution. Okay? And so we talked last time about how we would get the alpha primes and the beta primes. The alpha prime would be less than 0, the beta prime would be greater than 0, and we would have something like the integral from alpha prime to beta prime of e to the negative s. And we just put exactly what we had before. It was phi double prime of x naught over 2 y squared dy. So that was the integral we had, and we wanted to replace that with the Gaussian integral. Right? So when we did the change of variables, we got this, and then we got a small error term. The small error term had an extra factor of y. Essentially, the only contribution from this is contributes for the absolute value of y. About how large do you think absolute value of y can get and have this still contributing? About what would be your window? So if you look at what's going on here, you have an sy squared. Yeah, y should be about 1 over square root of s. Because if y is equal to 0, you have e to the 0. E to the 0 is 1. When y goes all the way up to 1 over square root of s, this is going to be something on the order of e to the negative of fixed constant. So it's going to decrease maybe by like a 1 over e or 1 over e to the 2015. It's going to decrease by a fixed multiple. Once y starts getting a little bit larger, if it was, log s over square root of s, then this would look like e to the negative constant times log of s. Negligible. So you expect contributions for y up to about 1 over square root of s. And that's why if you look at, I'm going to have to ask you to swivel again, so thank you, Alex. So if you were to look at over here, if you look at the error term is of size 1 over s, the main term is of size 1 over square root of s. The error term had this extra factor of absolute value of y from when we were doing all of our approximations. The reason that leads to an error term of size 1 over square root of s smaller is precisely for this reason. The contribution is essentially from values of s up to 1 over square root of s. And since it has an extra factor of absolute value of y, the maximum value of y in that region is 1 over square root of s. And so you can bound that second integral by 1 over square root of s times the value of the first integral. That's where this comes into play. Sometimes you can actually get a better error than this. And we actually get a better error than this in Stirling. But this is where that error is coming from. Okay, so now coming back, thank you. So coming back to what we were doing over here, we want to figure out what's going on. So if we were to just stop at 1 over square root of s, there would still be a little bit of a contribution. And the contribution would be of the same size. Because you could go from 1 over square root of s to 2 over square root of s. And if you go in a small region like that, the exponent here is still going to be of the size of some constant. It'll differ maybe by a factor of 4, but it'll still be of the order of some constant. So you really need y to be greater than 1 over square root of s by something growing in s. It doesn't matter how quickly it grows, any little bit. So now when we have alpha prime and beta prime, remember alpha and beta are fixed independent of s. So if you want to draw things not to scale, here's 0, here's 1 over square root of s, here's negative 1 over square root of s, here's 1 over s to the 1/4, negative 1 over s to the 1/4, here's beta, and here's alpha prime, here's beta prime. These are so far away because they're fixed that we are many, many standard deviations away. If you know Chebyshev's theorem from probability, that's enough to bound what's going on. Remember, alpha prime and beta prime are fixed. They don't depend on s. That's the key point. So we were worried about y up to a little bit more than 1 over square root of s. Well, beta prime is fixed, so once s gets enormously large, beta prime is so far above this, it's negligible. And so now what we're really doing is we're integrating a Gaussian over very small, we're integrating a Gaussian very far away from the mean. The standard deviation of this, if you write this as a normal, we wanted to have all of this y squared over 2 sigma squared. So sigma squared, the variance, is going to be 1 over s phi double prime of x naught. So the variance is 1 over s approximately up to some constant. The standard deviation is 1 over square root of s. That's exactly what we're getting here. We're moving on the order of the standard deviation. When you start moving multiple standard deviations away, the contribution becomes negligible. And in fact, even just Chebyshev, how many standard deviations are we to get from 1 over square root of s to, say, just the number 1? That's square root of s standard deviations. So beta prime is going to be on the order of square root of s standard deviations. How many of you have seen Chebyshev's inequality? Okay, so if you've seen Chebyshev's inequality, this is now square root of s standard deviation, Chebyshev gives you a 1 over s for the decay. Now, this is much worse. This is a horrible, horrible estimate, but it's enough to show that it decays rapidly in s. If you haven't seen that, what we can do is just do the integration. And so we can just integrate from 1 to infinity. Quick question?
No.
Okay, so we could just integrate from 1 to infinity of e to the negative y squared over 2 sigma squared dy. And now, right, so now we'll be basically doing some kind of change of variables. And so if we let t equal y over sigma, dt is dy over sigma. So what would we get now? We would now be integrating, dy becomes sigma dt, so we have a sigma outside. When y equals 1, t is going to be y over sigma, so it's going to be 1 over sigma. And now we'll have e to the negative t squared over 2 dt. But remember, as s gets very large, 1 over sigma is going to 0. So we're integrating at a very, very small place. So if you want, let's assume, is phi double prime of x please be 1? What's phi double prime? Phi double prime of x naught is 1. Good. So sigma is just 1 over square root of s. So our integral is now just the square root of s, the integral from square root of s to infinity of e to the negative t squared over 2 dt. And now we just need to evaluate this integral. Yes?
Is it a 1 over square root of s out front? Because you had a sigma out front.
Oh, okay, could be. Probably, yes. I will admit I'm not really caring what's out front because I'm so excited about what I have inside here. We have so much decay here that I'm not worried at all, but I think you're right that it is that. All right. So now if you look at what's going on here, we want to try to evaluate this integral. This is going to be less than or equal to 1 over square root of s, integral from square root of s to infinity, e to the negative t dt. Because when s is large, t over 2 is going to be at least 1. And now I can evaluate this integral nicely. This will be e to the negative square root of s. And so you'll get e to the negative square root of s divided by square root of s. So we can be very crude in the evaluations. That's the whole point of today's lecture. You don't have to be careful. This is why I didn't have to prepare my lecture ahead of time. Almost any approximation we do will work because we have so much decay. We are so many standard deviations away. If you know Chebyshev, this is one of the best chances in your life to use Chebyshev where you can be this crude. Normally, you are losing a lot of information. We don't care if we lose that much information. We have an e to the minus t squared over 2. We should be able to get a much better bound on how quickly it's decaying. This is terrible to replace e to the negative t squared with e to the negative t when t is large. This is extremely wasteful. You are throwing away so much of your decay. But if you look at what we're doing, this is the region where there's so little contribution, it doesn't really matter. The other error term we have is going to dominate this. So the other lesson from today is keep track of where the action happens. If you are away from where the action happens, don't be careful. Right? You're spending all of your time on things you don't need to. All right, so I'm not going to go through the rest of stationary phase. I hope that this is enough to give you an idea of how Laplace's method works. If you then want to see what happens if you let S be complex, you can just read, there's just like literally 2 more paragraphs in the book you have to go through. But the idea is you just bound the integrals away, and being extremely careless is typically fine. If you want to then get a general statement for NEC, that's where you have to do a little bit more work.